everyone. It is Friday, the 19th of December, 2025. It is also the new moon in Sagittarius. And I did share a video early in the morning yesterday. I didn't get online, but I was just sharing a video, and then I was gone right after that, gone all day. And anyway, very interesting developments and contacts reestablished. And but I'd be remiss if I didn't talk about this. This is from Laura Gochiaga. Anyways, it's about the MIT fusion physicist who was shot dead at 47 years old.
MIT fusion scientist Nuno Loureiro is found shot dead in his Brookline, Massachusetts home just days after announcing a major breakthrough in clean fusion energy. Then suddenly he's gone. Look, this man wasn't just a scientist, he was the keystone of plasma fluid dynamics. His work defied Einstein, aligning more with Tesla, Lorentz, and the other suppressed ether theory. No carbon, no radioactive waste, no meltdown risk, free limitless energy. You think that's allowed? He questioned the very structure of quantum mechanics and replaced it with plasma field logic, the kind of logic that breaks monopolies on oil, uranium, and centralized grid systems. Comment, scroll if you feel this was not random. Get your scroll scan. You'll understand why energy, frequency, and timeline control are always connected. Look, his fingerprints were on global energy projects, including ones tied to the US Department of Energy. His death wasn't just tragic, it was strategic. It was a message. Fusion is not allowed to go public until the right controllers can gate it. Look, ask yourself, why are the same networks who falsely claimed he was Jewish and pro-Israel the first to push narrative spin before facts were even verified? Comment, scroll if your gut told you something was off the second you saw this headline. Because
my gut, oh my God, it almost like fell to the friggin' floor. Okay, and so I'm just going to stop this for a second because I was looking into what he had discovered. His, this is not the one, the work he was doing. And it's very much aligned with the research that I've discovered and looked into, and so I'll just show you some of my videos here. Oh, is this the one? Okay, so all I did was just I just typed in magnetism for like my content, and so if you look at my Rumble channel Don189, you'll see here we've got here my Grok chat and other software programs, but talking about electricity, dielectricity, and magnetism. We've got here gravity, electricity, magnetism, hidden secrets of the cosmos, right? Because I think that what we're calling gravity is not correct. And anyways, I talk about these in these videos. And so missing secrets of magnetism, quantum physics, particle and wave, cold and hot fusion, things that he was talking about that goes completely against the narrative that's been pushed now for a very long time. And so we have here quantum physics, particle to wave. Okay, I already said that. Magnetism, Searle. So I've talked a lot about the Searle effect generator and how that could have been the patent or blueprint for the UFOs that were put in movies in Hollywood and things like that after he created that device. Hemisig, going to talk about other things. And current events, magnetism, radiation, and light particles analysis. Okay, so we have magnetism, proton spins, paramagnetic gases. Let's say here, I'm talking about other things. Sometimes I put in other major events that are happening because I am an international security analyst, but I still try to add in this stuff because I try not to lose focus because this is very important. And I would have liked to have talked to someone like Loureiro with his discoveries because yeah, that would have been so incredible. But again, I'm going to show you a video that he did in January that he actually did. And I have not seen it yet, but because he died, because of what he discovered and the research that he was looking into, I feel like it's in order to honor him, we still have to continue this, obviously. And why not me? Since I have a little bit more of an understanding of his work than people just coming on to it after his murder, if that makes any sense. So I talk about unlocking secrets of Tesla, Rodin, Harameen, Russell, Wheeler, and me. This was over 2 years ago that I talked about this. And so, yeah, if that doesn't get me, oh my God. Anyways, not a lot of views on this one though, 242 and over 2 years ago, literally the unlocking secrets of Tesla, Rodin, Hermine, Russell, Wheeler. The sun, mathematical proof the sun is local. John Searle and levity disks. So I talked about that as well. Let's see here. The trinity of electricity, magnetism, and dielectricity. Another one over 2 years ago. Again, I posted these on YouTube for years, but I got so many accounts deleted. But the truth about oil, petroleum, our second most abundant fluid, and this is Fletcher Prouty that's talking, and people do not want this information out either. So like, there's multiple things that he's been talking about that possibly got him murdered. And I do understand why, because the people that have the monopolies on the military, pharmaceutical, industrial tech complex, they do not want this information out, nor do the people that are part of the steering committees that think we're so dumb that we can't figure out the reality of what this world or cosmos actually is. So even people like NASA, or organizations that are rather like NASA, RASA, the IS, all of these organizations, unfortunately, at the top, they are grifters, and they're lying to us about the reality of the world because, again, there's strength in having secrets. At least that's what they think. I think it's absolutely horrendous that people do that, because I don't think anyone has the right to lie to us about the reality of our world, but they're doing that, and they're doing it for a grift and for power and control. And they realize if people did realize or uncover what people like he has been sharing, then again, it would be like the New World Order would not happen. Anyways, and people would get back into the books, get back into the research, and discuss and focus more on this Earth plane, because we are not going to Mars to populate Mars. It's not happening. It's a luminary. It is some kind of an orb, etheric luminary above us within the heavens or the sky, the atmosphere, whatever you want to call it, and not a friggin' planet that we can land on with a anyway. So just wanted to share some of the videos on that. That's just on magnetism. Let me see if you just do a tag or a search rather for plasma, because he talks about plasma too. Let's see what comes up. Okay, so plasma moon, greater world map, and macro climate change, vibes of cosmos and flat earth nations. It's one of my titles. Breaking news, plasma gold sun, plasma silver moon, noble gases, last supper. Again, these are just names of, I just try to make them sound interesting. Quantum physics, particles to wave, cold and hot fusion. It talks about plasma in there. Let's see here. Sonoluminescence. Yeah, that's so interesting. Convexity, blood plasma, seawater, sonoluminescence. I thought more would come up with that. Maybe I've hid some because, especially before going on Viva Fry, like I thought that people would like look at that content that I've done on the moon landings and my interpretations of this cosmos. I thought it would just be like too much for some people, unfortunately, and so I did hide them for a little while, and some of them I have like unhid. But it's frustrating that I have to do that just so that people don't think I'm freaking crazy. And I'm not. I mean, maybe a little bit, but we all are. Anyway, so I want to get into his work. But first I want to show an article that they did write. Okay. So this is him. I know his photo's already circulating everywhere. It has been for days. So Nuno Loureiro, professor and director of MIT's Plasma Science and Fusion Center, dies at 47. He was a freaking professor and director. Like, that's incredible. 10 years. Illuminate the physics occurring at the center of fusion vacuum chambers at the edge of the universe. Interesting. Okay, so he was a professor of nuclear science and engineering and of physics at MIT. Wow. In a letter to the MIT community, President Sally Kornbluth wrote, "With great sadness, I write to share the tragic news that Professor Nuno Loureiro, director of the Plasma Science and Fusion Center, PSFC, died early this morning from gunshot wounds he sustained a few hours before. In the face of this shocking loss, our hearts go out to his wife and their family." Oh, he did have a wife and family, wow. "And to his many devoted students, friends, and colleagues." Okay, so advanced scientists' understanding of plasma behavior, including turbulence, and uncovered the physics behind astronomical phenomena like solar flares. I've literally talked about this as well. Actually, even in recent videos about like the increase in magnetic in the magnetic field of the sun, depending on if it's at its solar maximum or solar minimum, and Anyway, so just look at those videos, including trivia. Okay, so he was the Hermann Feshbach 1942 professor of physics at MIT and was named director of the Plasma Science and Fusion Center in 2024. Okay, so his research on magnetized plasma dynamics, magnetized plasma dynamics, magnetic field amplification and confinement and transport in fusion plasmas helped inform the design of fusion devices that could harness the energy of fusing plasmas, bringing the dream of clean, near limitless fusion power closer to reality. Like, I wish I would have been able to communicate with him when he was still alive. I had communicated with people, and one actually person through Mark Sargent. I think it was last year, or the year before. Might have been two. No, maybe it was last year. But anyway, and it was someone that was doing their doctorate or something like that. But anyway, she had talked to me. It was only going to be an hour. We ended up talking for a few hours. She had so many questions, but she was like listening to a lot of the information I was sharing to her about this. Anyways, this Earth plane and Cosmos, and then she wanted another meeting, and so I did this all for free, and I was very happy to do it, and that was another couple of hours, and she really appreciated it, and I expand that outward to people that are working in these specific fields in any academic institution. I tried at Carleton University during COVID. I was in my fourth year for a cognitive science degree, but I was branching out, getting other courses because just like there was just so much pseudoscience being taught, and there was like so much resistance. And Carleton University is an absolutely far left institution that is absolutely teaching pseudoscience and just again just like indoctrination. Unfortunately, it used to be a good institution, but and so anyways, my second degree is on pause. And but anyways, I work in the U.S. Good morning, everyone. I guess it's still early, for a Friday, so people are getting up now. Anyway, I would love to expand on this, and so I would be interested in reaching out maybe to the institution, seeing like who else he was working with. Anyway, all of that stuff. And but it's unfortunate because in Canada, I have tried to get the attention of people within multiple different academic institutions, and or people that are like literal geniuses and they're working on like electrical engineering or mechanical engineering or certain types of engineering or physics and things like that. And I'm trying to share information with them, and they're just like not really receptive to it at all. Like even an aerospace engineer, I gave some stuff to, and he's like, mental health check. No, I'm actually quite fine. He wasted no time contributing to the intellectual environments at MIT, spending part of his first 2 years at the institute working on the vexing problem of plasma turbulence. I want to talk so much about that, but even Walter Russell with his connections of like gravity and electricity and magnetism, creating that sine wave, and how it kind of parallels or like it explains like the movements of like the sun and the moon within the sky, especially the sun, and how it impacts again like magnetic fields and on the earth, within the earth. And anyway, he talked about alpha particles as well. That was very interesting, and how I believe that with well, that's not what I believe. My research leads me to believe that these ionized gases or these alpha particles and other particles, these are what contain like this cosmos with these what we call toroidal fields. Again, we cannot leave this cosmos. It is a contained environment. I know that sounds crazy to people, but I'm more comfortable talking about this stuff because people are going to die risking their lives to get this information out. Then it's the least people can do. And I have a lot less to lose than a lot of people. Like I don't even have I don't have kids or anything. Okay, so this was from 10 months ago. So Nuno Loureiro, it's him. He's the one that's talking. Modern plasma physics and its applications in astrophysics, oh my goodness, and fusion energy sciences has come to rely heavily on state-of-the-art computation. I think we should go back to our more ancient advanced technologies, but many of the key discoveries over the last couple of decades in this field have been driven by advanced numerical simulations performed in the world's leading supercomputers, and the expectation is that further significant progress is tightly coupled to algorithmic advances and hardware improvements. Okay, it goes on from there. I have not done any real look into his work yet, and I have not seen this video. So we're watching this together. I have no idea what it's going to be about, other than the title. But we'll see.
Welcome everybody. Let me first thank you all for coming either in person or remotely. I hope everybody is okay, as well as okay can be in those times. So we're very pleased that Nuno came to us this week, Nuno Loureiro from MIT, where he's the director of the Center for Fusion Science and Plasma Physics. Nuno did his PhD in Portugal, in Lisbon at the IST, and then spent postdoctoral appointments in Princeton at the Climate Fusion Center, and then went back to Portugal to lead a research group before starting his position at MIT, where he is now. Nuno is a very, very accomplished scientist in plasma physics. He won the Thomas Dix Award for outstanding contributions as an early career plasma physicist. If you wonder what Nuno does mainly for a living, he solves a very, very good problem of magnetic recognition. The question is, how do magnetic fields dissipate energy? And then if you're interested in astrophysical plasma, also how do you accelerate particles in this way? So what actually makes many of the processes in the universe?
How's the sound for everyone? I don't know about that. I want to see if there's maybe a better video. If not, I'm going to go back to this and let's see here. So this was lecture 2. I wanted to go on lecture 1 first. This was the 2nd of September, 2025. Okay, so let's see if this one is better sound. Has better sound. No, that's Bruno. Loureiro. It's a different person.
Hello, hello. Can you hear me? Yeah, thank you. Okay, so welcome back. So before starting the second lecture, I would like to make some ratification from stuff that I said yesterday. So first one is that Siva brought to my attention yesterday that actually this.
Well, that's the only one on there for videos. Wow, they really scrubbed. Okay, so I'll keep this going. Maybe put on headphones or something to hear it better. Sorry about that.
Welcome everybody. Let me first thank you all for coming either in person or remotely. I hope everybody is okay, as well as okay can be in those times. So we're very pleased that Nuno came to us this week, Nuno Loureiro from MIT, where he's the director of the Center for Fusion Science and Plasma Physics. Nuno did his PhD in Portugal, in Lisbon at the IST, and then spent postdoctoral appointments in Princeton at the Climate Fusion Center, and then went back to Portugal to lead a research group before starting his position at MIT, where he is now. Nuno is a very, very accomplished scientist in plasma physics. He won the Thomas Dix Award for outstanding contributions as an early career plasma physicist. If you wonder what Nuno does mainly for a living, he solves a very, very good problem of magnetic recognition. The question is, how do magnetic fields dissipate energy? And then if you're interested in astrophysical plasma, also how do you accelerate particles in this way? So
Of course, my mic's off. I was going to say, I did find another video. I'm just going to shut this one down. I did link that video on the description, so you can watch that. But I did find another one. I want to just see if there's better sound with this guy. Because again, this is going to be an intro to me anyway, so it doesn't really matter what video I see of him first. It's going to be new to me, what he says. So hopefully this is better.
Okay. Well, thank you. Thanks again for the introduction, and thanks for the invitation. I'm delighted to be here talking to you guys. I would be more delighted if this was actually held in person. I love Porto. I would have loved the excuse to go there. Sadly, that's not to be. But let me anyway applaud the committee for organizing this against what must have been difficult odds, and everyone who's attending for trying to better oneself by participating in this event and making it a success. So again, nice to meet you, everybody, and I hope I won't be wasting too much of your time with my lecture, which is slightly ambitious in terms of its scope, and may not actually, I won't be able to do justice to all of these things that are alluded to in the title, but I'm hoping that I will be able to communicate at least some of the excitement about plasma physics in several of its sort of manifestations that I'm more familiar with. Cool. So if you wish to ask questions throughout the lecture, that's fine. I won't be actively monitoring the chat because I'll be, focused on the talk. But if something shows up, maybe the organizers can interrupt me and we'll clarify it as we go along. Cool. So I suppose, maybe I thought a good place to start is by giving everybody a more specific idea of what a plasma is and the sorts of complexities that arise when you're trying to study plasma physics. So here's what a plasma is. So plasma equals this person plus that person. I'm hoping that that you will recognize these two faces. So that's Maxwell and that's Boltzmann. And the reason I say this is that plasmas are a collection of interacting charged particles, many of them, and they interact via their mutual potential. And so to explain the interaction of this hot electron and ion gas, for example, you typically, you will need Maxwell's equations. And of course, because there's just so many of them, you're better off using a statistical description as provided by Boltzmann. Now, more recently, these two gentlemen also feature in plasmas that we are interested in, even though I won't talk very much about this. This person is Einstein, of course, and he is here because in many astrophysical applications, special relativity effects in plasmas are important, and oftentimes general relativity effects, such as, for example, if you're studying accretion around black holes or if you're studying neutron star collisions, these are all plasmas, and there you can't neglect relativistic effects. And in even more exotic cases, such as magnetars and pulsars, QED effects become important. And so Julian Schringer is here to do to show that that's also possible. Now, it probably won't surprise you that the combination of the theories worked on by these four people on your screen right now leads to something that's pretty complex. And if that's your intuition, you are correct. So plasma dynamics is indeed very complex and perhaps best described as out of equilibrium statistical electrodynamics, sometimes with relativistic effects and sometimes with QED effects. Now, plasmas do amazing things, and we study them both because they do amazing things and we are intellectually curious, and so as physicists, sometimes we're driven by the question itself and not necessarily its practical applications, but also because there are many practical applications of plasma science. So what you're looking at here is actually an example of both. This is the sun flaring. So you probably have seen images of solar flares before. What you're looking at is, so all of these contours here, I hope you can see my screen. These are actually, so this is actually radiation that you're seeing from the plasma in the solar corona. And the plasma is very strongly anchored to the magnetic fields on the surface of the sun. So it actually traces magnetic field lines. So these loops are loops of magnetic field. And because the photosphere, so the surface, if you will, of the sun is turbulent, these magnetic field loops are being continuously twisted by random foot point motion. And sometimes that leads to a lot of tension being applied to these magnetic fields. And their relaxation can lead to these explosive events, such as solar flares. So that's, of course, a fascinating thing to try to understand, how exactly does this happen? But if you're more engineering minded or more practical minded, these sorts of events launch highly energetic electrons that, in extreme cases, can actually fry satellites. And, that's a problem for communications on Earth, et cetera, et cetera. So it launches a discipline known as space weather, which tries to understand the Sun-Earth connection and what's going on there. And that, of course, at the heart of that is nonlinear plasma dynamics, such as you're seeing here. So let's talk a little bit about why plasma physics matters. So I said this already. It's interesting per se as an intellectual frontier of theoretical physics. Sorry, and sort of, by the way, the question that often arises is this. I sometimes explain to colleagues that a lot of plasma physics is pre-relativistic and pre-quantum, and they sort of stare at me in disbelief and think, how can that be any interesting? And well, it's interesting in the sense that out of equilibrium statistical electrodynamics is not a solved field by any means. And so that alone, so Maxwell plus Boltzmann, leads to enormous complexity, and that's quite enough to keep a lot of us busy. So I'm not overstating it when I say that it's an open intellectual frontier of theoretical physics. But in terms of sort of scientific and engineering questions, you may have heard of fusion as an alternative clean energy source, so much so that the National Academy of Engineering here in the US has chosen fusion as one of the grand challenges for engineering in the 21st century. And I'll talk more about this. Fusion at its heart, whether it is successful or not, depends on how much we can control the plasma and predict and understand its nonlinear dynamics. So that's quite a challenge. And then there's a lot of applications in astrophysics. And one of the ones that I will talk about a little bit is the origin of magnetic fields that pervade the universe. And that ties into the magnetogenesis problem and the dynamo problem, meaning the amplification of magnetic fields via plasma motions. Things I won't talk about so much are origin of cosmic rays, which are thought to be accelerated by plasma processes throughout the universe, black hole emission and jets, and a lot of other things like neutron star collisions, magnetars, etc. Many astrophysical environments are essentially plasmas that we try to understand, and that depend on. So our understanding of those environments depends on a clear understanding of plasma phenomena. And then people, of course, explore applications of plasma physics to things like tabletop particle accelerators achieved via, very powerful lasers, space weather that I've mentioned already. And then there's a whole industry surrounding low temperature plasma physics with a lot of, real industrial applications, but I will say nothing about that because that's not my domain, and nor do I have the time to explore it here. Okay, so here's a very brief introduction to plasma physics. So 101, as they would call it in the US's denomination for introductory courses. So, let me say, I say to you, a plasma is a collection of a large number of charged particles, and they're interacting, for simplicity, via their own Coulomb potential, right? So I have a particle here, they are at a certain distance. We can compute the force between those two particles, and, how do I solve the evolution of this system? You might say, well, that's very simple. I'll solve F equals ma for each particle. Trivial. Okay. So what do? I choose a particle. I compute the force on that particle due to every other particle in my system, and that gives me the acceleration. I'll move it forward, and I do this for every particle. So that's called an n-body problem. And you can do that if you have 2 or 3 particles. Computationally, you can do it if you have a few million particles. But there's many more particles than that in a plasma. There's in fact, billions and billions, right? And so this is not going to be a fruitful approach, because even though it is sort of the most rigorous approach, you're not going to be able to solve anything. Right? That's nor analytically, nor really computationally. And this illustration here is actually a simulation done by a high school student that was interning in my group. And this is just to show you the sort of complexity of electron trajectories that you can get in a plasma if you have a magnetic field that you impose that's varying sinusoidally as a function of time. Okay, so this picture here is, imagine that you give these electrons a magnetic field that you prescribe. This magnetic field varies as a function of time at some frequency, and you ask, what are going to be the trajectories of these electrons? And this is what you get. You see the electrons with random velocities initially, and you get this sort of behavior. As an illustration, I think it makes it quite clear that even sort of prescribed simple magnetic fields give rise to a lot of complexity. And magnetic fields in a plasma, when they are evolved self-consistently, easily become turbulent. Right? And so it's basically hopeless to think that you're going to be computing trajectories exactly for anything that approaches realistic conditions. Okay? So we don't do this, right? Because if you were trying to do this problem with an n-body simulation, you'd basically stop. You wouldn't be able to solve anything. So instead, like I said, we often adopt sort of a more statistical description. And here's Boltzmann equation, if you wish, where the acceleration is given by the Lorentz force, electric field plus a magnetic field acting on particles that are at position r with velocity v. Okay? So how do you solve this self-consistently? Well, you do it as follows. You say, I'm going to solve this equation, but I need electric fields and magnetic fields. Wonderful. So I know Maxwell's equations. Here they are. And by the way, they are written here in CGS units because we are strong believers in the fact that the electric field and magnetic field should have the same units. So we use CGS tendentially. So there you are. So that's it. So that's Maxwell. And then you say, well, but Maxwell depends on charge density and depends on current density. So how can I compute those? Well, you do that because charge density is the sum over all species of density times charge, and the density is just the integral over velocity space of the distribution function. And the velocity is the first moment. So this is a closed system, and it's a beautiful thing in a way, right? So you solve this equation to get F, you compute the current, and you compute the density, and the charge density, and the velocities. You plug that into Maxwell's equations. You compute the consistent electric fields and magnetic fields. You plug the whole thing back, and you solve again, and you iterate until you converge. Now, this is simple to state. Here's a simulation. What you're looking at is just one-dimensional in position and one-dimensional in velocity, and you're looking at contours of F. And there's some instability that doesn't matter here. Again, looks quite complicated, but just to demonstrate that we can do this simulation, and you're now evolving F as a continuous object, right, the distribution function, rather than thinking of individual particles, which is sort of a more challenging problem. Now, of course, this is a fully nonlinear system because to compute F, I need electric and magnetic fields, but to compute the electric and magnetic fields, I need to know F, right? So it's fully nonlinear. And F itself is a 6D object plus time, and that's incredibly unpleasant, of course. You are not going to make a lot of progress trying to solve this analytically. It is sort of very difficult. It took someone like Landau himself to solve the linear version of this problem and therefore derive what is known as Landau damping in plasmas. And it took a Fields medalist, Cédric Villani, recently, a mathematician, to show some interesting effects about the long-term behavior of the solutions to these equations. So, I'm not just name dropping. I'm saying this so to highlight the challenge in solving this equation analytically, or deriving a lot of insight from an equation like this. Now, you can take the extreme of opposite view. You can say, maybe I can think of this plasma as a fluid of electrons and ions interacting with each other, but I don't need to think about these particles. Maybe they're colliding enough, right? They collide all the time, and therefore they have a fluid-like character. The flow of this object, this plasma, is like water, except of course it now responds to the Lorentz force. And so if you adopt that, so assuming that there's enough collisions, the distribution function is approximately Maxwellian, you'd write equations like this, where rho is mass density, so this thing is like a continuity equation. This thing here is actually just F equals ma, right? So this is the momentum equation, where the forces acting on your fluid are pressure gradient, viscosity, Lorentz force. This is the acceleration. And then you need a diabatic equation of states, an equation for pressure. Again, you need to know the magnetic field, so you couple that with and these are called the magnetohydrodynamic equations. They're hydrodynamics, but now there's a magnetic field, so you refer to this as magnetohydrodynamics. And the first person actually, sorry, excuse me, I've been lecturing online for over a year now, and it's still difficult to get things right. Okay, so this is Alfvén, who was the person to coin this term, magnetohydrodynamics, and to first use these equations to derive a type of waves that is characteristic of plasma called Alfvén waves, disturbances in the magnetic field that propagate along the magnetic field. And for that work, he got the Nobel Prize in 1970. So just to summarize, these are two extreme views of the plasma. You either say, I'm going to solve Boltzmann equation for the distribution function. You do that if collisions are infrequent. Or you say, I'm going to solve the magnetohydrodynamic equations, and you do that if collisions are frequent enough. Now, unless you're a genius, it's very hard to get intuition from just staring at the Vlasov equation, the Boltzmann equation. But equations like this appeal very much to our intuition, because everybody has an idea of what a density is, or what the pressure is, or what the flow is, right, of water. I have a plasma flowing, I measure velocity at some position, I understand that concept, right? So oftentimes we try to work with these equations if we can, if for no other reason, just the fact that these are talking about quantities that you can measure and that you have a lot of intuition about. And also, oftentimes, well, not oftentimes, always, it's much easier to solve these equations on a computer than it is to solve Boltzmann, because of course, all of these quantities here, density, velocity, etc., these are quantities that are just three-dimensional, the x, y, z, whereas F was a 6D object, right? So in terms of computational costs, it's much easier to deal with these equations than it is to deal with the Boltzmann equation. So here's an example of something that these equations are used for. This is a 3D simulation of an accretion disk around a massive central object, perhaps a black hole. The object itself is not simulated, right? But the accretion disk is. And you see that these equations capture turbulence in this accretion disk, and that turbulence is why matter in the accretion disk accretes much faster to the central object than it would if the only thing causing your break of angular momentum, conservation was viscosity, because viscosity is extremely small in many of these accretion disks. Awesome. So now that I think I've set the stage, I'm sorry, I'm looking for a watch. Excuse me, just to keep track of time. Now that I've set the stage, we can talk a little more about the things in the title, namely some aspects of fusion and some aspects of magnetic fields throughout the universe. So let me tell you a little bit about fusion. So the sun shines because fusion happens in the core of the sun, right? And we've been trying to do that on Earth for quite some time now. Our problem is, of course, that we don't have the kind of gravitational pull that the sun has, right? So you can't very well just come up with an experiment in the lab where you're going to confine a plasma gravitationally by just having, some source of gravity there, right? So we're trying to do it with magnetic fields instead. And it all relies on taking some gas, right, and heating it up so that two nuclei can overcome their mutual repulsion, overcome the Coulomb barrier, and fuse. And in this particular case, for example, deuterium plus tritium, you get out an alpha particle, so helium plus a neutron. And the reason this reaction, this fusion reaction in particular, is the one that we most often consider has to do with cross section, and the shape of the cross section as a function of energy. And if you think that it's difficult to heat something to very high temperatures, what you seek is the reaction that's going to maximize cross section at the smallest possible temperature, right? So you could be doing it with helium-3, or you could be doing it with deuterium, but the reaction that has the highest cross section at the lowest temperature happens to be deuterium tritium. And so that's why we sort of do it. And the whole idea is very, very simple. This reaction produces an alpha particle with 3.5 MeV energy. It produces a neutron with 14 MeV energy. The neutron, of course, doesn't respond to electric fields or magnetic fields. So it comes out and you use it presumably to activate some sort of heat cycle. And the helium stays confined, and you hope to use the energy from the helium to keep your plasma hot. So a self-sustaining reaction. This is not easy to do. So ask yourself, how do I confine a gas of electrons and ions? So you try to put it in some container. Let's say it's some sort of cylinder. And of course, if you these random is in random direction, right? So they'll everywhere and eventually hit the walls of your device and recombine there, and you're out of plasma. So one way to do it is just say, well, let me have a magnetic field threading this cylinder. And I know that if I do that, the particles can move freely along the magnetic field, but perpendicular to the magnetic field, they have to go in Larmor gyrations. And so they're confined, at least perpendicular to the magnetic field. If I want them also to be confined along the magnetic field, all I have to do is turn the cylinder into a donut, right? Torus. And that's the whole idea behind sort of the most advanced schemes in magnetic confinement fusion. And we call this a tokamak. Here's the most recent conception of one in a model that MIT is proposing here called Spark. You're seeing a cross section, of course. This thing is a toroidal chamber that's been cut here in the drawing so that you can see the glow of the plasma inside. This is just a cartoon, of course. This is not a real experiment. We're building it now, hoping to have it working in 2025. Okay, so the gas is here, you heat it up, fusion reactions happen here, neutrons escape, and you get energy. It's a beautiful thing if we can make it work. But this is not easy. And one of the reasons it isn't easy is very easy to understand. Okay, so let me go back to this cross section here, and let me call your attention to this number, 100 keV. 100 keV is around 100 million degrees centigrade. So that's hotter than the surface of the sun. Okay. The sun doesn't have to worry about this, but we do because we want to maximize fusion reactions. And so we want to operate at very high temperatures. And so that means that on this drawing, there's going to be a plasma here, which at its center is sort of at, maybe 20 keV, okay? So 100 million degrees Celsius. But over here, well, there's going to be a material surface here, right? And materials are going to be at room temperature. So the temperature gradient from here to here is probably the largest temperature gradient in the entire solar system. Okay? It goes from 100 million degrees Celsius to basically, 30 Celsius. Okay? And this distance, this is a person. So this distance is about 1 meter, if that. Now, as physics students, you probably know that there's one thing that nature does not like, and that's gradients. Nature doesn't like density gradients, Rayleigh-Taylor instability. Nature doesn't like velocity gradients, Kelvin-Helmholtz instability. Nature doesn't like temperature gradients. Okay, and so when you set up a temperature gradient that's as large as this, things go wrong, right? And one of the things is that the plasma decides that it doesn't want to have that temperature gradient and sets up all sorts of instabilities that lead to turbulence. And so what you're looking at here is a simulation done by my colleague Nathan Howard, maybe 6 years ago now, of what that turbulence might look like as shown by contours of electrostatic potential. And this is multi-scale turbulence because it has components that are due to the ions and components that are due to the electrons. And the electron to ion mass ratio is about 2000, and square root of that is around 40, right? So the Lama radius of an ion is basically this big. The Lama radius of an electron is this big. And these two turbulences happening at different scales talk to each other and inform each other. And you can see it here. You see, so these big blobs that you see are turbulence on the ion scales. But there's fine striations on top of each one of these blobs, and that's turbulence at the electron scales. And the fact that these two turbulences talk to each other means that if you want to get this right, you have to simulate all of these scales simultaneously. So to give you an example, for those of you who are interested in computational details, this simulation, this one simulation, the cost of it was 18 million CPU hours. So that means that if you have 18 million CPUs, you'd run them all in parallel for 1 hour to get this. Okay? That's not how it's done. This is run on tens of thousands of processors simultaneously. So parallel computing, right, state of the art then, and leads to this incredibly complex scenario that we then sort of mine for data and try to make better sense of. Now, it's not just turbulent tokamak plasmas that are turbulent. Space and astrophysical plasmas are almost invariably in a state of turbulence themselves, even if the reason for that turbulence tends to be different from just temperature gradients. And so this beautiful illustration that you can see in my virtual background is a simulation of turbulence done by my former student, Gian Andrea in Cingolo, of turbulence in an accretion disk, simulated using sort of an equivalent of the Boltzmann description. So just to illustrate that complex turbulence like this abounds. You find it in fusion plasmas, you find it in astrophysical plasmas, and it's this turbulence that ends up setting the macroscopic properties of these media, right? So if I want to know how long it takes me to dissipate, to diffuse the temperature in this plasma, right? That diffusion is anomalous. It is set by the turbulence. It's not set by collisions of any means, okay? So that would be very, very small. The fact that this is turbulent means that your plasma is going to cool off much quicker than otherwise. Okay? Incidentally, when you put a drop of milk in your coffee, you stir it, so that you mix it faster, right? You're creating turbulence because that leads to faster mixing. Similar thing here, right? If you didn't stir, it would take a long time for that one drop of milk to turn your black coffee into gray coffee, right? So if you stir it, if you give it turbulence, it's so much faster. So same thing in a fusion device. Sheldon, of course, understands turbulent transport perfectly. So I put this up as a bit of a joke, as sort of a for kicks, right? But it's actually quite interesting that they actually got a fusion expert to write what's on the board here. And so it's interesting to go through this. So what Sheldon is estimating here is the ion diffusion coefficient, basically how fast you lose temperature because of this turbulence. And he's still talking about the temperature gradient. You see, 1/T the TVR, that's the normalized temperature gradient in a tokamak. And down here, it's explaining something that actually is correct. He's saying, well, I have these turbulent eddies, but if somehow I can break them up, maybe because there's a shear flow, they become smaller. And if they're smaller, then that means that my turbulence diffusion becomes smaller. So that's what Sheldon is explaining here. So I thought you might find that amusing. Now, turbulence isn't the only instability that plasma.
I don't know if you can hear me. I can hear the video much better when I have these on. But I'll take this off. All right, because he was talking about another expert, and Alf Venn, I did want to share a little bit of information regarding him. Because again, this is another person I had no idea existed until literally now. So I've just been doing like a little bit of looking into him and stumbled upon this on Instagram, and then some other information I'll share as well.
And Tesla had a love child, it would be Hannes Alfvén. Born in Sweden in 1908, electrical engineer and physicist, has his PhD, the father of modern plasma physics. In 1970, he wins the Nobel Prize in Physics for his work in magnetohydrodynamics. Say that 5 times fast. Basically, plasma physics. You really just don't like talking about plasma. He made predictions in the 1930s that then were proven true in the 1970s and 80s. Insane. Pause the video and read what he has to say in his Nobel Prize lecture. He's talking about the electric universe. Now pause it and read that. He gets the Nobel Prize.
In order to understand the phenomena in certain plasma region, it is necessary to map not only the magnetic but also the electric field and the whatever currents. She's asking us to read it, but her face is in the way. But anyways, space is a network of whatever which transfer. I'm assuming energy and momentum over large or very large space. Structure. But anyways,
He warns them, hey, this plasma out here, these electric currents, these magnetic fields, they matter. You need to look at this. If these astrophysicists are not actually looking at the real data, not looking at these theoretical models, they're going to miss all of this.
Yep.
He warns this in 1970.
If they look at their current theoretical models, so we're going to miss this. And he's talking about astrophysics. I've been saying as well that people that I know that are astrophysicists, really famous ones, I've heard them talk and describe the cosmos and astronomy and so many things. And I've shared this, and I'm showing actual scientific data to actually debunk what they're saying. So I don't understand how they get so much friggin' money, all of these speaking engagements, and they're sharing pseudoscience.
We are 2025, and the only reason I've heard of him is because I'm into this stuff. Now you've heard of him too. Go look up everything he said and did, because it is truly amazing. They always bury the guy that's too far ahead. I'm resurrecting you, buddy. Let's go.
Okay, he was the first to show. Okay, so he proved that space isn't empty. It's filled with plasma that carries electric currents, generates magnetic fields, and forms waves, now known as Alfvén waves. Anyway, experimentally confirmed both in labs and space, as in like this atmosphere within. He was first to show frozen-in plasma and magnetic fields. I've talked about that. Locked together in cosmic movement, field-aligned currents, electric currents powering auroras and Earth's magnetosphere. I've talked about that. Later imaged by satellites. MHD correctly scales from labs to cosmic structures, rivers of electricity shaping what they call galaxies. But again, this is within this contained environment. These are just light shows within the sky. He proved it, built it, and won a Nobel Prize for it. But after the prize, astrophysics shrugged and kept spinning its gravity-first narrative. Very interesting. Every major breakthrough Alfvén warned about, from auroras to cosmic filaments, was confirmed, yet still gravity first prevails. Very interesting, because it should not. And I'll get into a little bit more of his work because I did mention Birkeland current. So a Birkeland current usually refers to the electric currents in a planet's ionosphere that follows magnetic field lines, i.e. field-aligned currents, and sometimes used to describe any field-aligned electric current in a space plasma. They are caused by the movement of a plasma perpendicular to a magnetic field. Birkeland's currents often show filamentary or twisted rope-like magnetic structure. They are also known as field-aligned currents, magnetic ropes, and magnetic cables. Originally, Birkeland currents referred to electric currents that contribute to the aurora, but I think that these are electromagnetic disturbances or interactions within the atmosphere caused by the luminaries, specifically the sun and moon, more the sun. But anyway, caused by the interaction of the plasma in the solar wind with the Earth's magnetosphere. Correct. The current flows earthwards down the morning side of the Earth's ionosphere around the polar regions. See, again, this is where like people are not understanding it. The whole picture, even missing one little part, it unfortunately screws people up. And okay, anyway, so spacewards up in the evening side of the ionosphere. These Birkeland currents are now sometimes called aurora electrojects. The currents were predicted in 1903 by Norwegian explorer and physicist Christian Birkeland, who undertook expeditions into the Arctic Circle to study the aurora. Okay, so the reason why they're particularly interesting is that in the plasma force to carry them, they cause a number of plasma physical processes to occur: waves, instabilities, fine structure formations. These in turn lead to consequences such as acceleration of charged particles, both positive and negative, and element separation such as preferential ejection of oxygen ions. Both of these are electrons. Like ionized gases, again, it's like the absence or the removal of electrons, making it more proton dominant. But anyways, both of these classes of phenomena should have a generalized astrophysical interest far beyond the understanding the space environment of our own Earth. So there's that. I have them open on different tabs. So there's synchrotron radiation is electromagnetic radiation similar to cyclotron radiation, but generated by the acceleration of ultra-relativistic, i.e. moving near the speed of light, electrons through magnetic fields. This may be achieved artificially by storage rings in a synchrotron, or naturally by fast-moving electrons moving through magnetic fields in space. The radiation typically includes infrared, optical, ultraviolet, X-rays. The radiation was named after its discovery in a General Electric synchrotron accelerator built in 1946 and announced in May 1947 by Frank Elder, Anatol Gurewitz, Robert Langmuir, I don't know how to pronounce that, and Herb Pollack, in a letter entitled Radiation from Electrons in a Synchrotron. Again, even with that, like it would be the absence of electrons. So I'm reading this, but again, there's some things in here where like it's either I'm not getting it because I'm not smart enough, which is likely the case, or it doesn't resonate with me just because of my interpretation, which you can see in my previous videos regarding radiation, protons, electrons, etc., etc. Non-thermal emission by radio astronomers. Okay, anyway, very interesting. More on the guy. Hans Alphen. I'm going to look more into his work for sure. I'm guaranteed if he was at Carleton University, he wouldn't have got his degree either. He'd be like, nope, can't have this. He was a Swedish scientist who is considered one of the founding fathers in the field of space plasma physics. He made many contributions and discoveries associated with both terrestrial and cosmic plasmas, not always acknowledged by his peers. He won a Nobel Prize theory of plasmas called magnetohydrodynamics. He originally trained as an electric power engineer and later moved to research and teaching in the fields of plasma physics. Alphen's contributions to plasma physics include theories describing the behavior of aurora, the Van Allen radiation belt. I've described these as well in videos. The effect of magnetic storms on the Earth's magnetic field. I've talked about that. Magnetic and electric fields and cosmic plasmas. The terrestrial magnetosphere and the dynamics of plasma in our galaxy. They're very interesting. different interpretations of what this galaxy is, argue that if plasma pervaded the universe, which means was spread throughout the universe or this cosmos contained, it could then carry electric currents capable of generating a galactic, or the toroidal fields that contain this environment, magnetic field, a cosmic magnetic field, the toroidal fields, Van Allen belts, whatever you want to call them, that is what it is. Okay, so after winning the Nobel Prize for his works in magnetohydrodynamics, he emphasized that in order to understand the phenomena in a certain plasma region, it is necessary to map not only the magnetic, but also the electric field and the electric currents. Space is filled with a network of currents which transfer energy and momentum over large or very large distances. Okay, that's actually what was in the Instagram video, but she was obscuring it. So the currents often pinch to filamentary or surface currents. The latter are likely to give space, as also interstellar and intergalactic space, a cellular structure. But again, we have different interpretations of what that actually is. All right, so very interesting, and I'm going to be digging more into him as well. Yeah. There's so much going on regarding world events right now, especially Canada. It's such a shit show, and I don't want to take away from this scientific video, but even Vasi, like she did an interview with Pierre Poilievre, and she was just such a nasty person. She was just so nasty and uninformed and just disgusting, and it just shows like there's not even a lot of like conservative journalists that work within the mainstream media, and this is why more and more people, these social media influencers and podcasters are getting so successful and have way more views, and so he is better served to just completely like never talk with Vasi again. Because like again, it's just rewarding bad behavior, and she doesn't support the conservative movement at all. Like she is literally, anyways, like a Doug Ford, like a fake conservative, and not helping at all. And so he has like there's so many different social media platforms he can go on where he'd get a lot more attention. And I said that even during his election campaign, he should get out more. And but I said I understand why he doesn't want the mainstream media to follow him because they lie. And so no matter what he does, no matter how nice he is, no matter how informed he is, no matter what doesn't matter. They're going to still paint him in a negative light, and the conservative parties, because it's a grift. And they keep on lying again about so many things as well. So, I mean, I think that like the Mercedes Stevensons and the Vassis, like these fake conservatives that actually destroy it from the inside and fuck it up, like respectfully speaking. Again, why do we platform these people? That's just a rant. Yeah, she was so nasty, and she was so ill-informed, and you had two people that are literal traitors to their constituents that cross the floor, which by the way should not be allowed. There should be some kind of a constitutional argument, like some kind of like a constitutional lawyer that challenges this, because there are a lot of people within these ridings that are very upset that he switched sides. And again, he can now vote as a liberal. That's not what they wanted at all. And so he was saying that he was listening to his constituents. I'm talking about Ma and others. That is a lie. He is a grifter. People have talked to people in his riding, I think it was Markham or whatever, and they are really upset about this. And so if there was an election now, he would not be an MP. And so this has nothing to do with Pierre's leadership. And again, I have definitely questioned things that he has done and said in the past. And I did not vote for the Conservatives in 2021. I voted PPC. It was to send a friggin' message, like we are not supporting like people that are not conservative in platform or ideologies or anything like that, and not voting for what Canada actually needs right now. And so, and then they started shifting gears a little bit with their narrative on COVID and immigration and things like that. But it took, again, that unfortunately. And I'll reiterate again, like he lost in his riding because like the district lines were moved in 2023 after the 2021 election. People got very strategic, and unfortunately there was destruction, and realty companies again that were demolishing protected lands and heritage sites, but they were like building these cookie cutter homes in these areas for people that were coming in, largely obviously immigrants and people coming in for government, but vote liberal. And so like his riding was inundated with a lot of liberal voters that he had never had before, not only because of the population increase, but also because of the district lines moving, and where he inherited more people that voted more liberal in his district, right? It was more in the eastern and like the northeastern end of his district, and so it was a grift, and people want to use that. Fine, but again, it just makes you sound ignorant. And then with the ballot scandals and stuff like that, and all the misinformation from legacy media, and even now, no one's calling out Carney. Like Rosemary Barton, Mercedes Stevenson, and Bassi, like they are literally just honestly people that they don't come across as radicals, but what they push is, unfortunately, and I think they should be fired. I know I've said it 10,000 times, so I will stop and I'll carry on with this.
Plasmas have to,
More interesting.
fusion plasmas have to contend with. There are, so as it happens, turbulence is sort of benign because, okay, so you lose temperature and particles and energy faster than you expect, but it doesn't lead to any major disruption of your fusion device. But you can also get sort of the tokamak equivalent of solar flares. And these are like macroscopic disruptions. So here's a filament that's about to be expelled from the plasma, very much like the solar flare that you saw at the beginning. And that launches a lot of particles, very fast particles that can then hit the walls of the device and do things like this. So this blob here, that's, those tiles have been melted by extremely fast electrons that were produced by the plasma. So this you cannot have, right? Because eventually, do more of these, you will actually pierce a hole through the wall, right? And that's basically the end of your experiment. And so, there's this fascinating complexity and myriad modes of ways that things can go wrong, right? All these instabilities that we have to somehow master, both at sort of, if we can, at the theoretical level, but at least with simulations that set an operational space for fusion devices. Right? We know we can operate in some parts of that operational space, but not everywhere, because many of these, many values of parameters lead to instabilities that will then cause things like that, and that's unacceptable. Cool. So there isn't only the magnetic type of fusion, magnetic confinement. Another variety that I won't say very much about is inertial confinement fusion. This is a completely different concept. The idea here is that you have a pellet, maybe sort of a pellet is something that is sort of marble-sized, and it contains deuterium and tritium, and you put it inside of some chamber, and then you use extremely powerful lasers to, if it's indirect drive, as they call it, these powerful lasers hit the walls of some confinement chamber, called the hole round. That creates X-rays, and then the pressure of those X-rays is supposed to make the target compress and generate enough pressure that you can fuse the contents. Okay. Now, does this work? Not yet, and it's easy to understand what might go wrong here. So here's a simulation, and okay, so think you have a balloon, and now you have fingers trying to compress that balloon, right? And you know that if you compress here, the balloon will expand elsewhere, right? So what you try to do is to have many fingers compressing that balloon as uniformly as possible. Okay? And that's hard, right? To achieve that degree of symmetry so that you result in uniform compression rather than, compression here, expansion there. That's a very difficult thing to do. So what you're seeing here is basically instabilities that are driven inside of this capsule by virtue of the fact that the irradiation by these lasers isn't actually uniform. So this is very much research in progress, as is magnetic confinement fusion, and it leads to all sorts of interesting physics that go beyond just looking at the actual fusion itself. And here's one of the interesting aspects of these laser plasma interactions, or laser target interactions. So many times what happens is when you shine a laser at a solid target, so in this case the solid target would be sort of at the bottom of this blob here, of this green blob. So you shine the laser, you ionize the target, and you have an expanding cloud of material coming towards the laser. And then you have a temperature gradient, because if you're closer to the laser, you are hotter, right? And if you're further away, you're colder. But you also have a density gradient because if you're closer to the surface, you are more dense. If you're further away, you're less dense. And as it happens, there's a battery mechanism that is generated by virtue of the fact that the temperature and the density gradients are not aligned. They can be perpendicular to each other. That's a battery that generates a magnetic field. And what you're seeing here is a simulation by Kevin Scheffler, who's a postdoc working with me some years ago, showing how when you set up that green blob, as it were, right, a blob of density with a temperature gradient that's perpendicular to the density gradient, you generate these magnetic fields like this. Okay, so that's called the Biermann battery effect. And people do this routinely in laser plasma experiments, but it is also thought that this same mechanism, the Biermann battery, is responsible for generating seed magnetic fields throughout the universe. Maybe because you have a supernova explosion that drives a shock front, and at the shock front you can have density and temperature gradients that are misaligned and generate magnetic fields. So this is sort of the jumping slide where I go from talking about fusion to talking about magnetic fields in the universe. So we use magnetic fields on Earth here to confine plasmas, but elsewhere in the universe, magnetic fields are just there. And the only thing that seems to be as ubiquitous as plasmas in the universe are magnetized plasmas, right? So magnetic fields are found literally everywhere and at all scales. So of course, Earth has a magnetic field. This is a famous simulation of what that magnetic field might look like by Glatzmeyer 20 years ago. That magnetic field of the Earth interacts with magnetic field coming at us from the sun and generates a very complex magnetospheric structure that essentially protects us from very, very fast electrons, very energetic electrons coming at us from the sun, right, and generates what's called the magnetosphere. Very complex environment. The sun, of course, has its own magnetic fields. And then you start going to larger and larger scales. So here's a galaxy. This is M51. And this is supposed to be tracing the structure of the magnetic field in the spiral arms of that galaxy. And then you say, well, what about galaxy clusters? Are there magnetic fields at the scale of galaxy clusters? And the answer is yes, there is. You take galaxy clusters and you try to measure magnetic fields around them, and you find that this magnetic field exists and is organized at the scale of the clusters themselves. So this is fascinating. It reveals, sort of this ubiquity of the magnetic field in the universe prompts many questions. One of them is, where do they come from? Because, so I'm not an expert in string theory or anything like that, but the conventional wisdom these days is that magnetic fields themselves weren't really created at the Big Bang, right? So there has to be some sort of plasma-based mechanism by which you are going to create these magnetic fields, essentially from nothing. And the Biermann battery that I just talked about is one possibility. You generate some sort of seed magnetic fields. And then you ask what happens to them as the plasma sort of moves and evolves these magnetic fields. So let's talk a little bit about that. So all of these environments, the Earth's core, the sun, solar system, the interstellar medium, galaxies, galactic clusters, they're all plasmas. You can think of all of these environments as plasmas. And so if you can think of them as plasmas, you might want to write down an equation for how a plasma evolves a magnetic field. And so I flashed this equation earlier. This is Ohm's law for a plasma. You might recognize it without this term. It just says electric field equals resistivity times current. When you were in kindergarten, you saw voltage equals resistance times current, right? So this is sort of the differential version of that. This electric field equals resistivity times current. But of course, the plasma is moving. So what you have to do is you have to write down the electric field in the frame moving with a plasma, which is electric field in the laboratory frame plus U cross P. You combine this equation with Faraday's law, so you take the curl of this, and curl of E is minus dp dt, so you get the induction equation. So this equation tells me how the magnetic field will evolve in a plasma subject to flows, plasma velocity U, plus resistive diffusion. Okay, so without this term, this is nothing but the diffusion equation, like the heat equation. But this term is quite interesting, and it gives rise to non-trivial behavior of the plasma, of the magnetic field in a plasma, and in particular, can lead to amplification of that magnetic field. That's so-called the dynamo problem. One curiosity about this equation is that it's linear in magnetic field, in B. So if your magnetic field is initially 0, all you're ever going to get out of this equation is 0. So you need to provide some seed for these flows to operate on. And that seed is maybe coming from the Biermann battery, but there are other plasma-based processes that might also give a seed like that. Okay, let me ask the organizers, how long should I speak for? Do I have another 5 minutes, perhaps?
Yeah, 5 minutes is all right.
Okay, thank you. Good. So I'll be quick from here. I don't need to speak forever. Let me just present you with a very simple estimate. Let's just have a magnetic field present when Earth formed. Now you think that the outer core of the Earth is an MHD fluid, it's a plasma, okay? And we know what its properties are. So you know that based on the properties of that fluid, if you had a magnetic field present when Earth was formed, it would take about 10 to the 5 years for that field to ohmically diffuse. But we know from paleomagnetism, so essentially measures of the magnetic field on Earth, that the Earth has had basically a constant magnetic field for essentially however long it's existed, around 10 to the 9 years. So you conclude from this that the only possibility is if the Earth actively generates its own magnetic field. Right? So the motions of the core of the Earth are such that via the induction term, they continuously generate the magnetic field of the Earth so that this term cannot just dissipate it away. Okay? And that's sort of a demonstration of the need for a dynamo on Earth, but it's similar for the Sun and similar for many other magnetized planets and stars. More recently, we're trying to go beyond this MHD description of dynamo and actually look at dynamo in collisionless plasmas. And that's very complicated. It's computationally very difficult and analytically also very difficult. My student Muni Zhu is working on this. This is the first simulation of a completely ab initio first principles dynamo. You can see that you sort of start with nothing and very small scale fluctuations arise, and then there's some sort of complicated dynamics. They start merging and creating larger scale magnetic fields, and so on and so forth. So just to point out that this is very much ongoing research. The dynamo problem is far from solved, especially if you're looking at it in a collisionless plasma. Let me skip this. Plasma physics has recently met quantum computing, so there's this idea that quantum computing can offer exponential advances in speed-ups in computing power. Plasma physics requires vast computational resources, but it's fundamentally nonlinear, so it's not at all obvious that you can use quantum computing to solve plasma problems. This is something that I'm working on and happy to talk about it in more detail if you have questions. I'll skip this. These are two Portuguese physicists working here in the US, applying very sophisticated machine learning techniques to try to come up with more sophisticated models to simulate plasmas with and understand plasmas with. I'm also happy to answer questions about this. Let me just put up my summary slide and state that I hope to have convinced you that plasma physics is intellectually rich and broad in scope. There's many opportunities for deep theoretical contributions and for cutting-edge computing. The success of fusion is critically dependent on understanding nonlinear plasma dynamics, as is the understanding of a wide range of astrophysical environments. And, supercomputing has been one of the pillars of plasma science, so there's theory, there's experiments, there's observations, but, over the last 20, 30 years, with the dawn of advanced supercomputing, we've really made great progress. And maybe we're at the dawn of a new scale because exascale computers are coming up, machine learning, quantum computing. So stay tuned. I expect that the next decade is going to bring, quite significant advances in this area. So I'll stop here and thank you all for your attention, and I'm happy to entertain questions. Thank you.
Thank you for a very interesting talk. We have quite a few questions in the chat, so I'll give the word to the participants right away. So the first one is from Thibault. You should, let's see if this works right now. So you should be able to turn on your camera and microphone and ask a question.
Can you hear me?
Yeah.
My question was a bit simple, and it was on slide 6 when you present the Maxwell equations. I was wondering why do you not why there wasn't the displacement current on the J on the fourth equation?
Well spotted, Thibault. You get kudos for paying attention. Well done. I didn't write the displacement current because I was focusing on the sub-relativistic limit. And so if you are at velocities that are much smaller than the speed of light, that term is small. Okay, so you don't need it. But if I was worried about relativistic effects, I would have to keep it. So that's the answer.
Okay.
Good question. Thank you.
Thank you for your presentation. It was amazing.
Thank you.
We have another question. I think you already answered this one, but I'll ask them to ask. So Andres asks about the number of CPU hours. I'm not sure if you want
I'm happy to talk
elaborate on that. So
yeah,
Andres, you should have just, if you want to turn on your camera. If not, I'll just ask. Well, they're not responding. So Andres just asks, I think it's one of the very first simulations you showed. How much time did that simulation take in terms of CPU hours? If I remember, it was one of the...
So this one right here, maybe was the first. I think the simulation is about 2 million CPU hours. I can't read it because the Zoom thing is on top of it. So let me answer maybe that question more generally. So state-of-the-art simulations in plasma are upwards of 1 million CPU hours, always, okay? Now, whether they are 1 million or 20 million or even 100 million actually depends on the types of equations that you're solving. So for example, if you're solving something that looks like the Boltzmann equation, there is, because dimensionality is higher, you can explore more CPUs, right? So the higher the dimensionality of the problem, or the larger the number of particles you have, the more CPUs you can use. So it's not uncommon these days that kinetic simulations of plasma can take something like 20 million CPU hours for one simulation. Okay, if you're doing MHD like here, your opportunities for using more CPUs are smaller, also because the codes don't scale perfectly, if you know what I mean. So, if you double the size of the problem, that doesn't mean you can use twice as many processors. So there, the simulations tend to use fewer computational hours. But perhaps the most interesting point, right? So this is not just.
Before we get into his most interesting point, I don't know if you can hear me. I'm going to share something else that I think is very interesting from Alpha Van. Magnetohydrodynamics, I just wanted to get more into that, is the academic discipline which studies the dynamics of electrically conducting fluids. Examples of such fluids include plasmas, liquid metals, and salt water. The word magnetohydrodynamics, MHD, is derived from magneto, meaning magnetic field, and hydro, meaning liquid, obviously, and dynamics, meaning movement. The field of MHD was initiated by Hans Alfvén, for which he received the Nobel Prize in Physics in 1970. The idea of MHD is that magnetic fields can induce currents in a moving conductive fluid, which create forces on the fluid and also change the magnetic field itself. I do understand and agree with that. The set of equations which describe MHD are a combination of the Navier-Stokes equations. I'm not familiar with that, or maybe I am and I just forget. Again, that's why I do videos, so that it's on the record and I can go back to it to refer, because it's impossible to retain everything. Anyways, fluid dynamics and Maxwell's equations of electromagnetism. These differential equations have to be solved simultaneously, either analytically or numerically, because MHD is a fluid theory. It cannot treat kinetic phenomena, i.e. those in which the existence of discrete particles or of a non-thermal distribution of their velocities is important. Ideal and resistive MHD. The simplest form of MHD, ideal MHD, assumes that the fluid has so little resistivity that it can be treated as a perfect conductor. In ideal MHD, Lenz's law dictates that the fluid is in a sense tied to the magnetic field lines. That, again, interesting. To be more precise, in ideal MHD, a small rope-like volume of fluid surrounding a field line will continue to lie along magnetic field lines. The connection between magnetic field lines and a fluid in ideal MHD fixes the topology of the magnetic field in the fluid. For example, if a set of magnetic field lines are tied into a knot, then they will remain so as long as the fluid plasma has negligible resistivity. Resistivity. This difficulty in reconnecting magnetic field lines makes it possible to store energy by moving the fluid or the source of the magnetic field. The energy can then become available if the conditions for ideal MHD break down, allowing magnetic reconnection that releases the stored energy from the magnetic field. And I do believe that the sun is smaller, more local within this contained environment, possibly, and that it absolutely impacts the aurora bar, the light shows in the sky, the magnetic fields, depending on if it's at its solar maximum or solar minimum. There's a weaker or stronger magnetic charge, and that causes, again, more light shows in the sky, spread out over longer periods, and earthquakes for some reason, and more tornadoes and natural disasters around these times at the solar maximum. Anyway, this is often accomplished with approximations to the heat flux through a condition of adiabaticity or isothermality. Applicability of ideal MHD to plasmas. The plasma is strongly collisional, so that the time scale of collisions is shorter than the other characteristic times in the system, and the particle distributions are therefore close to Maxwellian. The resistivity due to these collisions is small. In particular, the typical magnetic diffusion times over any scale length present in the system must be longer than any time scale of interest. We are interested in length scales much longer than the ion skin depth and Larmor radius perpendicular to the field, long enough along the field to ignore Landau damping, and time scales much longer than the ion gyration time. System is smooth and slowly evolving. The importance of resistivity. In perfectly conducting fluid, the magnetic field can generally move through the fluid, following a diffusion law with the resistivity of the plasma serving as a diffusion constant. This means that solutions to the ideal MHD equations are only applicable for a limited time for a region of any given size before diffusion becomes too important to ignore. One can estimate the diffusion time across a solar active region from collisional resistivity to be hundreds to thousands of years, much larger than the actual lifetime of a sunspot. So it would seem reasonable to ignore the resistivity. By contrast, a meter-sized volume of seawater has a magnetic diffusion time measured in milliseconds. And so talking about seawater as well, I've talked about how the luminaries do impact saline water and for the ebb and flow, tidal waves, things like that. But it's just very interesting to me how fresh water that doesn't have the salt in it, how it's not touched. And so I've done videos on that. Okay, so this means this, yeah, okay, so even in physical systems which are large and conductive enough that simple estimates suggest that we can ignore the resistivity, resistivity may still be important. Many instabilities exist that can increase the effective resistance of the plasmas by factors of more than 1 billion. The enhanced resistivity is usually the result of the formation of small-scale structure like current sheets, or final-scale magnetic turbulence. They're calling it magnetic turbulence, sure. That's basically what they can say is caused when the sun travels on its circular ring path. And we're getting close to the winter solstice, where the sun will be traveling the Tropic of Capricorn, its outermost ring, 23.4 degrees south latitude of the equatorial ring, and where we will be experiencing the longest nights and shortest days in the northern hemispheres, where over 90% of the population resides. What was I? The enhanced resistivity is usually the result of the formation of, okay, did I already say that? When this happens, magnetic reconnection may occur in the plasma to release stored magnetic energy as waves, bulk mechanical acceleration of material, particle acceleration, and heat. Magnetic reconnection in highly conductive systems is important because it concentrates energy in time and space so that gentle force applied to a plasma for long periods of time can cause violent explosions and bursts of radiation. When the fluid cannot be considered as completely conductive, but the other conditions for ideal MHD are satisfied, it is possible to use an extended model called resistive MHD. This includes an extra term in Ampere's law, which models the collisional resistivity. This is so interesting. Anyway, generally MHD computer simulations are at least somewhat resistive because their computational grid introduces a numerical resistivity. The importance of kinetic effects. Another limitation of MHD and fluid theories in general is that they depend on the assumption that the plasma is strongly collisional. This is the first criterion listed above, so that the time scale of collisions is shorter than the other characteristic times in the system, and the particle distributions are Maxwellian. This is usually not the case in fusion, spaced and astrophysical plasmas. When this is not the case, or we are interested in smaller spatial scales, it may be necessary to use a kinetic model which properly accounts for the non-Maxwellian shape of the distribution function. However, because MHD is very simple and captures many of the important properties of plasma dynamics, it is often qualitatively accurate and is almost invariably the first model tried. Effects which are essentially kinetic and not captured by fluid models include double layers, a wide range of instabilities, chemical separation in space plasmas, and electron runaway. In many MHD systems, most of the electric current is compressed into thin, nearly two-dimensional ribbons termed current sheets. They can divide the fluid into magnetic domains, inside of which the currents are relatively weak, or like non-existent. But anyways, current sheets in the solar corona are thought to be between a few meters and a few kilometers in thickness, which is quite thin compared to the magnetic domains, which are thousands to hundreds of thousands of kilometers across. Another example is in the Earth's magnetosphere, where current sheets separate topologically distinct domains, isolating most of the Earth's ionosphere from the solar wind. Okay, so resistive MHD describes magnetized fluids with non-zero electric diffusivity. This diffusivity leads to a breaking in the magnetic topology. See, that's not non-zero, I would say, like, anyway. The absence of electrons, ionized gases, and the movement through these magnetic fields. extended MHD describes a class of phenomena in plasmas that are higher order than resistive MHD, but which can adequately be treated with a single fluid description. These include the effects of Hall physics, electron pressure gradients, finite Larmor radii in the particle gyro motion, and electron inertia. Okay, so describes plasmas that include a non-negligible electrical field. That's interesting. As a result, the electron and ion momenta must be treated separately. I agree with that. This description is more closely tied to Maxwell's equations as an evolution equation for the electric fields. As an evolution equation for the electric field exists. Weird sentence. But anyways, in 1960, M.J. Lighthill criticized the applicability of ideal or resistive MHD theories for plasma. It concerned the neglect of the Hall current term, a frequent simplification made in magnetic fusion theory. Hall magnetohydrodynamics takes into account this electric field description of magnetohydrodynamics. So I'll take a look at him as well. Geophysics. The fluid core of the Earth and other luminaries is theorized to be a huge MHD dynamo that generates the Earth's magnetic field due to the motion of the molten rock. Okay, so I don't entirely agree with all of this. I get what they mean, but I do believe that there is some kind of a magnet at the center of the Earth that interacts with the luminaries above us, but like very much so, like more so the sun and the moon, but more the sun, and that it's through like that core, like the center of our Earth plane, that is what creates, again, like the toroidal fields, these magnetic fields, these Van Allen radiation belts at the extremes. And I do believe that these luminaries, these etheric orbs, whatever you want to call them, Eudoxus, again, look at his work. I've shared his work before as well. These circular ring paths that these 7 luminaries or 7 wandering stars, or anyways, these lights in the sky, I do believe there's sonoluminescence involved in that, and cymatics. Sonoluminescence for the sun and moon, and cymatics being utilized for the luminaries possibly. And their movements on these circular rings, again, there are largely within like the Mazzaroth, there's a zodiacal belt, and depending on the seasons and the years and the months, their ring paths, again, they do change, they do shift to be closer to the center and then outwards again, and so even the sun as well, there's a misinterpretation of it being tidally locked to the Earth and orbitally locked and 237,000 miles away, or it's just I don't believe in any of these things as well. I've given my reasons why. And I do believe that they are electromagnetic in nature, and anyway, impact us in varying ways, but from within this contained environment, within this cosmos. And that's where we tend to like divert, right? When I try to engage people like this, it's because I don't believe that the sun is 93 million miles away, and anyways, and what they're saying it is. And I've given my own proof for that, by the way, as well as multiple different declassified documents from multiple different institutions, from the government, from NASA, from aerospace engineers institutions, and what they say this cosmos is, to varying degrees. Anyways, the fluid core of the Earth and other luminaries is theorized to be huge MHD dynamo that generate the Earth's magnetic field due to the motion of the molten rock. Again, okay, so such dynamos work by stretching magnetic field lines that thread through the turbulent or sheared flows in a conductive fluid or through the ether. The total length of magnetic field line is a particular volume determines the strength of the magnetic field. So stretching the field lines increases the magnetic field. Yeah, you gotta stretch the field lines. And I believe you can only do that with a moving magnet. Astrophysics. MHD applies quite well to astrophysics since over 99% of baryonic matter content of the universe is made of plasma, including stars, the interplanetary medium, space between the planets. Again, I call that ether. The interstellar media. Okay, anyways, it's just getting too much for me here. Okay, so sunspots are caused by the sun's magnetic fields. As Joseph Larmor theorized in 1919, the solar wind is also governed by MHD. The differential solar rotation, may be the long-term effect of magnetic drag at the pole. Anyway, magnetic drag on its ring path, and MHD phenomena due to the Parker spiral shaped assumed by the extended magnetic field of the sun. Again, I don't know about that. Look more into it. Okay, closed systems such as the cloud of gas and dust from the sun was formed. Plasma confinement, liquid metal cooling of nuclear reactors, and electromagnetic casting, among others. Very interesting. In early 1990s, Mitsubishi built a boat, the Yamato, which uses a magnetohydrodynamic drive, driven by a liquid helium-cooled superconductor and can travel at 15 kilometers per hour. Yeah, liquid helium. Power generation fueled by potassium-seeded coal combustion gas showed potential for more efficient energy conversion. The absence of solid moving parts allows operation at higher temperatures, but failed due to cost-prohibitive technical difficulties. Trivia: the ebbing salty water flowing past London's Waterloo Bridge interacts with the Earth's magnetic field to produce a potential difference between the two river banks. Michael Faraday tried this experiment in 1832, but the current was too small to measure with the equipment at the time, and the riverbed contributed to short-circuiting the signal. However, the same process, Dr. William Hyde Wollaston was able to measure the voltage induced by the tides in the English Channel in 1851. I don't really know. That sounds vaguely familiar, these tests that were being done. Okay, so the first recorded use of the word magnetohydrodynamic is by Hans Alfvén, 1943. Wow. Well, I would argue that the Egyptians and people that predated the Egyptians, people from ancient advanced civilizations that have built structures that we cannot even come close to recreating today, I do believe that they absolutely had these capabilities, and we can see that within the ruins and the excavation sites and materials that have been preserved, and some of them are still even hidden from us underneath museums, underneath the Vatican, these catacombs, and these other, and even rich, like the super rich, right? They like even in their own homes, or places that they own, they do have a lot of historical artifacts that would be incredible for the public to have access to. As the term electromagnetic hydrodynamic waves is somewhat complicated, it may be convenient to call the phenomenon magnetohydrodynamic wave. Sure. Anyway, I just thought that was interesting. But I do like magnetism. It's almost over.
About bragging about how many CPU hours we can use, right? The more interesting point is that even though we're doing these incredibly large simulations, they are still much, much, much smaller than the realistic systems. So, you know, no computer is actually big enough to simulate things that are happening in the solar corona. Okay, so I'll give you, this is best parameterized by using the Reynolds number. The Reynolds number is basically a ratio of, so it's size times velocity divided by viscosity. The Reynolds number in the solar corona can be something like 10 to the 12. Okay, the Reynolds number that you can simulate is like 1,000 or maybe 10,000. Okay, and that's proportional to the resolution you can have, basically the size of your computer. So we are many orders of magnitude below what we need to actually provide a realistic simulation of anywhere. Okay, so that, I think that sets things in context and tells you why exascale is so interesting to us, as is machine learning and maybe quantum computing.
Yeah, I think that's answered. It being many hours of many orders of magnitude below where we need to be is the story of my PhD. So we have another question by, well, two questions actually by Imanj. So I asked that you just ask one of them just so we can give opportunity to someone else. But yeah, I think.
Yeah. Sir, could you explain how exactly does the misalignment of the temperature and pressure density gradients generates a magnetic field?
Yeah, good question. So I just stated that, right? But I didn't explain it. To explain that requires. So the idea was simple. I just said, let there be a temperature gradient and a density gradient that are not aligned, and that somehow magically gives you a battery, right? But I didn't really explain where that comes from. So I'm not sure that I can do justice to that without writing more equations. But the idea is like this. So you see this equation here? I said this was Ohm's law, okay? This is actually not complete. This is a simplification. This Ohm's law, if it were complete, would have another term here on the right-hand side, which would be the electron pressure gradient, a term like this, but for the electrons, okay? Now, you remember maybe that I took the curl of this equation to arrive at the induction equation. When I take the curl of the pressure gradient, this would be the pressure gradient divided by density itself. There's going to be a surviving term that looks like grad n plus grad t. And that term is going to be a source for magnetic field. Now, if you're looking for some intuition, it just has to do with the fact that having a temperature gradient and a density gradient generates currents in my plasma, so electron flows, which then lead to a magnetic field. So that's maybe not the most satisfactory answer, but that's the answer I can give you without writing more equations.
Yes, sir. Thank you, sir. I understand.
Good. Thank you.
Great. Thank you. We have another question from Alec. So let me just find you. Oh, here we go. Oh, sorry.
Can you hear me?
Yeah.
So my question is, in the last slides, you mentioned that the Earth's magnetic field was constant in the last billion years.
Roughly.
So, yeah, is it right that the Earth has lost 10% of its magnetic field in the last 150 years? And how
Yeah.
come?
So, excellent question, Alec. Thank you. So, when I say the Earth's magnetic field has remained roughly constant, what I mean is, if you look over longish timescales, its magnitude is roughly constant. So of course, it varies, right? And it reverses sometimes, right? And those reversals of the Earth's magnetic field, so reversal meaning the North Pole becomes the South Pole and vice versa. So those happen, and there's even interesting stories you can tell about how those reversals of the Earth's magnetic field correlate with mini ice ages and things like this. Okay, but the idea is that if you average over these periodic reversals, right, or fluctuations, the amplitude of the field has remained roughly constant. Okay? And the idea is that if there was no induction, if there was no dynamo working, you and I wouldn't be talking, right? The magnetic field would have diffused very quickly, right, within 10 to the 5 years. The Earth would be left without a magnetic field, and the Earth's magnetic field protected from cosmic radiation, right? And if you were open to that radiation, we
don't know what it protects us from because this is a contained and enclosed system, and we do not know what's beyond it.
Nor would I.
Yeah, thank you very much.
Great, and I think we have one last question, so I'll just give them.
Hello.
Yeah. Hi.
So my question was, where exactly at using quantum computing in plasma physics problem, as quantum computing is pretty new, right?
Yeah. Great question.
So how can we use it in plasma physics?
We can't. Okay. So the short answer, we cannot. Okay. The longer answer is that people are thinking like this. People are thinking it may take 20 years for there to be a quantum computer that one can use, right? Like one that actually is useful for something, for solving a real problem, right? And it's a mistake to wait 20 years and then start thinking how to use it. Because it's not going to be about taking a code that I have and just porting it to the quantum computer, right? That's not how it's going to work, because it's a fundamentally different architecture. So what people are thinking is, yes, it will take 20 years to get the computer, but it probably will take 20 years for us to understand how we can map our problems into something that can be solved on a quantum computer. Right? So the idea is to have the two lines of thought develop in parallel, so that by the time that there is actually a useful quantum computer, we are ready to use it. Okay? And it's actually a very challenging problem, because, like I said, all our problems are nonlinear. It's not at all obvious how you...
I think the biggest challenge, honestly, is that we don't have an appropriate model or frame of reference that is being utilized within these academic institutions. And so they're getting to the right conclusions for the most part, but they're operating from, again, I'm going to say, like an inaccurate model. And I will share just an example of just like throughout history, ancient civilizations who had depicted what they believe this cosmos to be, or this universe. And I did throw this on multiple software programs. I've done videos on it, and just to verify with these software programs, these AI programs, if these were accurate representations of what these different civilizations and cultures, how they interpreted the cosmos. And it was largely accurate. There may have been like one or two where there was just like small inconsistencies, but for the most part, like again, these were good. Again, these are just like symbolic representations, interpretations, right? And so even when I asked Grok and other software programs to recreate different models of the universe based on various different interpretations, it was way worse. Way worse. I showed that as well, just how nonsensical these images were. And yeah, so this being an enclosed system with the luminaries within traveling on circuit paths, like people like Eudoxus and others like him were discussing, and this being a gaseous pressurized environment. And so based on the second law of thermodynamics, like this, necessarily you need this to be a contained environment in order for that to even be achieved. And so that's just like another point out of many for that. And so I know that this throws a lot of people off and makes it look like I am some kind of a tinfoil hat wearing conspiracy theorist. At this point, I am okay with that, unfortunately. Just to try to get, again, more headway on this. I think if people understood that more, if you had people like Austin Whitsitt and others actually like be involved in panels or committees within these communities, just to give like different data, I think that this is something that like, it wouldn't be recreated in 20 years. It could be almost immediate.
You devise a quantum algorithm that will allow you to solve nonlinear problems. So, for example, an example of something I'm playing around with is called the Madelung transformation, which is a transformation you do to the Schrodinger equation that maps it into fluid-like equations. That's very interesting. Okay? It has limitations, but it's very interesting because our MHD equations are similar to those. Okay? So this gives you an idea of the type of mapping that you can do to some problems that might make them easier to solve on a quantum computer. But it's a completely different way of thinking to what we do currently with conventional computing. Like, you don't think like that for conventional computing. So that's the answer.
Thank you.
I think that's also, with that said, I think we can close this session. Thanks again for the very interesting talk.
This was, it's over. This was posted 4 years ago. May 2021. Wow. Yeah, so 4.5 years ago. And how many views here? Less than 20,000 views. Wow. Yeah, this is information that people are, I get it, they're not interested in. It's probably boring to a lot of people, but I think it is important. And it's interesting that he was also talking about oil. And I've discussed that as well. Again, look at the video I've shared multiple times that Fletcher Prouty put out there, and the rabbit hole I went down with that. And yeah, anyways, on that note, I will leave it at that. And I hope that everyone has a wonderful rest of your day.